Hey everyone, today we're going to peel back the layers on something you interact with literally every single day, but probably never think twice about: coating adhesion. We're diving deep into the microscopic science that decides why the paint on your car sticks or, why sometimes it fails spectacularly. So let's get into it and uncover the science that's basically holding our world together. Have you ever actually wondered what's holding it all together? You know, that protective layer on your phone screen or the special coating on a medical implant. It all comes down to this constant, invisible battle being fought right there on the surface. So what's the secret sauce? What makes a bond strong enough to actually last? So here's how we're going to tackle this. We're going to treat it like a scientific mystery. First, we'll introduce the hero and the villain of our story. Then, we're going to crack the case by looking at the forensic tools scientists use. After that, we'll line up the usual suspects behind why coatings fail, check out the engineering breakthroughs that fight back, and finally, we'll ask, what does the future hold? All right, first up, every good story needs a hero and a villain. And in the world of material science, this epic struggle happens right at that tiny interface between a material and its protective coating. So meet our hero, adhesion. This is that fundamental force that anchors a coating to the surface underneath it, what scientists call the substrate. And our villain? Delamination. This is the absolute worst-case scenario, when that heroic bond breaks and you get peeling, flaking, a total breakdown of the surface. Our mission is pretty clear. We gotta empower the hero and figure out how to defeat this villain for good. So, when a bond does fail, how in the world do scientists figure out what went wrong? I mean, they can't just eyeball it. They need some pretty specialized tools to gather clues from what's basically a microscopic crime scene. And their number one forensic tool is the scratch adhesion test. And trust me, it's just as aggressive as it sounds. Scientists literally take a sharp point and just scratch a surface, but with more and more force, pushing it right to its absolute breaking point. For something as critical as a dental implant, researchers like Madera and his colleagues use what's called a progressive load test. They ramp up the force all the way to 100 newtons. They have to be sure that coating won't fail when it really, really matters. And if you look here, you can see failure isn't just a single event. It's more like a catastrophic chain reaction. It all starts with, number one, cohesive cracking. That's when these tiny fractures start appearing within the coating itself. Then the real trouble begins at number two. The coating starts to physically lift away from the surface. That's interfacial delamination. And finally, it all ends with number three, chipping or spallation, where chunks just break off completely. Game over. But get this, scientists can zoom in even further, practically listening for these tiny signals of stress. A small pop-in sound is actually, well, it's not great, but it's a good sign. It means the material is bending under pressure, but the bond itself is holding on. It's the pop-out that they dread hearing. That's the smoking gun. That's the sound of the bond actually breaking and critical delamination starting. Okay, now that we know how to investigate the crime scene, let's meet the culprits. These are the main reasons that adhesion gets weakened and delamination takes over. Here's our rogues gallery. First up, you've got porosity. Think of it like microscopic potholes that just create weak points all over the bond. Then there's thermal mismatch. This is a constant tug of war, where the coating and the surface expand and contract at different rates until they basically rip each other apart. Improper surface roughness is another one. It can sabotage the bond by not giving the coating enough to grab onto. Hydrothermal aging is that slow, sneaky damage that just comes from exposure to heat and moisture over time. And finally, there's residual stress, a hidden tension from the manufacturing process itself, constantly trying to pull the coating away from the inside. And this quote right here really drives the point home. As these researchers explain, those tiny little pores aren't just sitting there. No, they can actually trap corrosive gunk that actively attacks the bond from the inside out, making failure almost inevitable. It's a small flaw with huge consequences. Okay, so we've identified the bad guys, but science, of course, is all about solving problems. So let's look at how engineers are fighting back, designing coatings that can actually withstand all these attacks. And scientists are fighting back with some really incredible strategies. If you look at this table, you'll see one method is just adding a bit of copper into certain nickel coatings, which dramatically boosts their hardness. Another cool technique is called surface functionalization. It's basically custom designing the surface chemistry to create a way stronger, more stable chemical bond. And maybe the most impressive one, researchers can now grow interlocking crystals right at the interface. It creates this powerful mechanical lock between the coating and the surface. It's like microscopic Velcro.
So why do we go through all this trouble? Why does this tiny microscopic battle of adhesion versus delamination matter so much in our big macroscopic world?
Well, because the stakes are incredibly high, strong adhesion translates directly to high performance. It means much better durability so we can make products that are actually built to last. It means critical safety, especially for things like medical implants, where failure is just not an option. And yeah, of course, it also means better aesthetics, a surface that stays smooth, clean, and looking good for years.
At the end of the day, the science we've been talking about isn't just stuck in a lab. The strength of this invisible microscopic bond is what guarantees the performance and safety of some of our most advanced technologies, everything from the implants inside our bodies to the composite parts that let airplanes soar through the sky.
And that leads us to one last really fascinating thought. We've gotten really good at making bonds stronger, but the next frontier is making them smarter. As our understanding of all this deepens, are we heading towards a future where coating doesn't just resist a scratch, but can actually sense the damage and heal itself? The battle on the surface, well, it's far from over.